So in this video, we are going to discuss the parallel stub matching. Again, to reiterate, the purpose of impedance matching is whenever there is an unmatched load in the end of the transmission line, we would attach a matching network along the transmission line so that the impedance seen by the source would be equal to the characteristic impedance itself, right? So that is the purpose. So that there will not be any reflection over here and the impedance seen by the source will be equal to Z0 itself, right? So there are two ways in which we can perform single stub tuning. Right? One was a series stub tuning, so for which you'll find the link in this video, right? Video's description. So the second one is parallel stub tuning. So in this video, we'll concentrate on parallel stub tuning. So in single stub tuning, we had preferred impedances because when you have more than one impedance, so it is, if you have them in series, all you need to do is just to find the total impedance. It is just sum of two impedances, right? So similarly, for parallel circuit, when you have two admittances, basically just the inverse of impedance values, I'm just writing it over here as y1 and y2. The net admittance seen over here will be just sum of the admittance values, individual admittance values, right? So if impedances are given, we just need to take the inverse of impedance to find the admittance. That's the basic concept. Now, just similar to the series stub, we will operate everything except for all the impedance points or all the points in the Smith chart that we will utilize will be for with respect to the admittances, right? All the impedances that we will look at, all the impedances that we plotted in series stub matching. Here we'll use parallel stub or shunt stub matching, right? Parallel stub concept. Now, wherein we'll go for the admittances one, right? So again, we have a load of characteristic, of a particular impedance that is not matched. So we will find what is the admittance using this expression. Inverse of impedance will be admittance. So we'll normalize it by using this expression YL by Y0. And we would be obtaining this, this in the Smith chart. Either you can solve it and then plot, or other aspect is you plot the ZL, normalized load impedance, and in the opposite, diagonally opposite point in the VSWR circuit, the impedance value would read the admittance value, right? So again, I'll explain that when we go to that aspect. So I'll explain that, right? So again, from the load location at a particular distance, you would find a point where the admittance reads, the normalized admittance value would read 1 plus or minus JB. And what we would do, we would attach a stub, right? So input admittance seen at that point at a distance of D from the load location, the input admittance should be 1 plus or minus JB. We will try to find out along the VSWR circuit. And at that point, we will attach a parallel stub. Now, parallel stub, one end can be either open circuit or short circuit. And based on the stub length, our admittance value should be cancelling out the reactant susceptance. In admittances, we call it as the real part as conductance. The real part we call it as conductance, and the imaginary part we call it as susceptance, right? So the susceptance needs to be cancelled out with the use of this stub. So you have open circuit stub. So one end will be open circuited. So the admittance that this stub is going to contribute would effectively cancel out the susceptance that is available in the Yin, which is having a real value, which is the conductance value as 1, right? We'll go through this in the slides so that you'll understand more further. I mean, as we move, right? So just give me a minute. Right. Again, we'll go to the steps wherein shunt stub are used for microstrip line or strip line, and series steps are used for slot line and coplanar waveguide applications. So single stub tuning, there are two aspects that we need to find out. One, what is the distance D from the load location, right? The load is located at a particular, at the end of the transmission line. So from there, at a particular point, as we move along the VSWR circle, as you're moving along the transmission line, you're moving along the VSWR circle. We need to find a point where admittance, the normalized admittance, is going to have a value, something like 1 plus or minus JB. So once you find out, there we'll attach an open circuit stub, right, or short circuit stub. It can be whatever is needed. So open circuit or short circuit, right? So that stub will be attached, and that stub's length will be tuned in such a way that the length would produce an input impedance or input admittance of stub, Y stub, that would effectively cancel out the imaginary part of this susceptance of our Y-in value, right? So that is the basic concept. So we'll go through this again in the steps. So we'll select the length D such that from the load, we'll identify a point D where our admittance will be, the normalized admittance will be 1 plus or minus JB. Can be the first step. So here values are not normalized. If you normalize it, Y value will be 1 plus or minus JB. Right? And the stub we'll select the stubs. We'll either start from open circuit or short circuit point, and then right from the open circuit or short circuit, whatever we choose, from the open circuit point or the short circuit point, whatever stub we select, we need to create, or we need to identify or tune, right? This is open or short. The length needs to be tuned so that the admittance of the stub will be equal to minus or minus of the susceptance. Basically, this is the susceptance value. So we'll try to cancel it out. So again, they're not. In actual values, we'll have plus J capital B and minus J capital B. Basically, the canceling out factors. But in Smith chart, we will go for the normalized values only. So we'll go into the problem directly, right? So we'll take a problem where the load impedance would be given as ZL is 60 minus J 80 ohms. So that's written out here. So I'm just writing it adjacent to 60. Right? So we need to design two solutions for single stub. Again, the stub that we are going to work right now is with respect to short circuit. So please note, in the previous video where we had discussed the series stub, we had the open circuited stub. But right now, just for the difference, we'll start with the short circuit over here, right? So shunt tuning, please note, shunt stub or parallel stub are one and the same. Shunt tuning is the parallel tuning that we are going to use. Basically, parallel stub we are going to attach and match to a 50 ohm line. When we have a statement as 50 ohm line, the characteristic impedance is 50. So ZL equals capital ZL upon Z naught. So when we substitute, we'll get a value of 1.2 minus J 1.6. Now, in the Smith chart, let's say you draw a Smith chart. You take a Smith chart and you plot this in real circle. So in real circle 1.2, right? Along the horizontal axis 1.2, right? So that will have the real values as 1.2, and minus j 1.6 will be somewhere over here, something like this, minus 1.6j, right? So our impedance point will be available over here, and if center of Smith chart is 1, now with this as center, with 1 as center, and the impedance point as radius, when you draw a VSWR circle, connect the center and this line and extend it to the opposite side where it intersects the VSWR circle. So that at that point, the impedance value will read an admittance value of the load, which is normalized. Right. So this one again we had discussed in the Smith chart problem video. So you can go through that. The link will be provided in the description. However, we also have this input impedance expression along the transmission at Z0 times ZL plus J Z0 tan beta L upon Z0 plus J ZL tan beta L. So this expression is there, right? So when we substitute the L value as lambda by 4, lambda by 4 corresponds to moving along the VSWR circle for 180 degrees, right? When we substitute this L as lambda by 4, we'll get an input impedance, which is not normalized, right? So the input impedance, when normalized to characteristic impedance, will be equal to the inverse of the load impedance that has been normalized, right? At L equals lambda by 4. Meaning from the load, so in the drawing what I have done, so the load is located at this point, right? I have marked it over here, I have circled it over here, right? So when we connect the center of the Smith chart and this point and extend it to the opposite side of the VSWR circle, the impedance value which you are reading in the Smith chart is going to be the normalized admittance value, right, which is YL. So since we are going to deal with parallel stub, we will mark all the values in terms of admittances, right? So all the Smith chart values, we will consider that the complete Smith chart value is going to represent only admittance values once you convert the load impedance to the load admittance using this step. So we again do that with the actual Smith chart. So let me select. So first step, we are marking the load impedance point, which is the real circle. So we have the horizontal axis of the Smith chart, and 1.2 is available over here, right? So that 1.2 circle, when you draw, right? So the real value is 1.2 throughout the circle, and imaginary value is basically the reactance values minus J 1.6. So the minus 0.1, 0 is this center, right? Central axis, then minus 0.1, minus 0.2, minus 0.3, minus 0.4, like this. All the values are listed out here. You'll be able to see, right? So basically this circle is minus 0.3 circle, this circle is minus 0.4 circle, minus 0.4 J, right? So the reactances basically are having the circles below. I mean, the negative reactances are all the circles that are below this horizontal line, and all the circles that are above the horizontal line represents the positive reactances, right? So now minus J 1.6 is over here along this in the Smith chart, right? So this blue color circle which goes towards this right side of the Smith chart, right? So this circle, it is basically minus 1.6 J circle, right? The intersection of minus 1.6 J circle and the real circle is 1.2, right? Which was yellow in the green, I've just highlighted in red, right? So the intersection of this point is going to represent the normalized load impedance, which is ZL. Now immediately draw the VSWR circle, right? So with center as 1 and radius as the distance from your characteristic impedance point, which is the Z0, which is equal to 1. With that as center and the distance between the characteristic impedance and the load impedance as the radius, you draw the VSWR circle and connect the center and the load point ZL and extend it to the opposite side to reach the VSWR circle. At the other side, where the impedance value that we are going to read on the Smith chart, we will get it as the admittance value, which is YL, normalized admittance value, which is YL. Right? We have converted the load to admittance. Now, what is significance is, see, the load impedance ZL is there. Now, what we are doing is, so as you move along the Smith chart for a distance of lambda by 4, input impedance is going to read, Zn is going to read at L equals lambda by 4. The normalized input impedance will be equal to the normalized load admittance, right? So for Smith chart purpose, we have moved to this point where your load's admittance is located over here. Now, what we are going to do is we are going to assume that this point is going to represent the load because we are looking at the admittance. So when you transform it into admittance, your starting point is going to be available over here, right? So this point would be the starting point corresponding to the load location. Please note, we have transformed the impedance values, load point to the, load admittance point to the, load impedance point to the load admittance. Henceforth, we are going to deal with only admittance. So consider the Smith chart as admittance values utilizing the existing Smith chart, right? All the points in the complete Smith chart are going to represent admittance values. Now, this is the first step, very important step for parallel stub tuning, right? From impedance, we are just transformed to admittance plane, right? Now, YL value is, it can be obtained using the Smith chart. Again, you can mark what is the real value. Real value will be somewhere over here, right? This circle. And imaginary value will be passing over here. And you can mark the imaginary value over here and real value in the horizontal axis wherever the real circle passes through. Okay. Now, I'll just clear this part. Just give me a second. Right. So we have the admittance point marked over here, right? So you can take the reference location of load as connect the load point and the center point and extend outwards wherever it strikes in the outermost circle. So that gives you the reference location of the load. So in the transmission line, we are looking at the load position in terms of admittances, YL. That's why I'm writing it as well. So the load's reference point will be this one. Now, as you move along the Smith chart, as you move along the VSWR circle at different points, all the admittance values represent all the input admittances that you are seeing at different locations along the transmission line. It is just similar to the impedances which were plotted in the earlier case, right? So as you move along the transmission line from the load towards the generator, so in Smith chart, you are basically moving along clockwise direction in the VSWR circle, right? In clockwise direction, and all the values that it takes are going to represent the respective input admittances. Now, as in the previous case, we need to identify a point where admittance is 1 plus JB or 1 minus JB. So for finding that, we need to draw the 1 plus JB circle. So how to draw it is with center, take the compass, with 3 as center and 1 to 3 as radius. When you draw a circle, that is going to pass through this real value 1, right? So this circle has real value 1 and it will take all the possibilities of the susceptance. the JB value, right? B value will be all susceptibles passed through this 1 plus JB. Now, the point of intersection of the VSWR circle and this 1 plus JB circle, we'll mark it as 1. At the first point, we are marking it as 1. And as you move further in the VSWR circle, starting from the load, if you move further, right, in the VSWR circle, when you reach the next point of intersection at 1 plus JB circle, right? So we get a point where admittance value is 1 minus JB, right? So this point we'll mark it as 2. So there are two possibilities where the impedance value or the, where the admittance value is going to be. So from load location at first, I mean, when you move along a particular distance, first you are reaching Y1 point where you are getting 1 plus JB as admittance. So this will be with respect to Y1 point. Now, instead of this, what you can do is, again, you start from the load location, which is YL. You move further, and at a particular location, you are going to get an input admittance as Y2, which is equal to 1 minus JB. In both the cases, real part is 1, imaginary part is either plus JB or minus JB, right? So we'll solve for both. So we need to find the distance D from the load along the VSWR circle, which has the admittance value as 1 plus JB. Where is this 1 plus JB? So that is basically, we are trying to identify these 2 points of intersections, which I just told, Y1 and Y2, right? So what is the distance from YL to Y1 and what is the distance from YL to Y2? Now, how do you find it out? So Y1's reference point, so with the center point, which is the characteristic impedance Z0, right? So I'm just marking the Z0 out here with the center point as reference and the load point as another reference. So connect these two and extend the line, right? Use a scale and mark and extend the line starting from the center of the Smith chart to the load and extending outwards. Now, in the wavelengths to the generator scale, whatever value is there, you mark it, and that will correspond to load's location. Right? That is a reference location of the load. Now, the point Y1, as you move along the Smith chart, as you move along the VSWR circle or as you move along the transmission line from load location, right? From the load location, as you move along, you will reach a point where input impedance is 1 plus JB, right? So reference point over there is, so connect the center point and that Y1 and extend outwards. So whatever is that value, so that value will be the reference location corresponding to Y1. Now, this difference between these two reference locations will give you actually at what length from the load you are going to find it, right? From the load, at what distance along the transmission line are you going to find the value 1 plus JB? Now that can be obtained using the difference between these two values, right? So I've just marked it over here, right? So this way you'll get the solution or the location where we'll get the 1 plus JB value. So in the as I told you in the previous case, the load is located at 0.066 lambda, right? Connecting the center point and the load point. When you extend to the outermost circle, we are reading a value of 0.066 over here in the outermost circle, right? Wavelengths towards the generator. And similarly for Y1 is located from center, connect to Y1 and extend outwards. Whatever value you observe is basically the location of Y1. So the distance between load and Y1, the difference, right? 0.176 minus 0.066. So that difference will give you the distance from the load location where you will read an input impedance of 1 plus JB of this format, where 1 plus JB is 1 plus J 1.47. So how do we get 1 plus J 1.47? Real value is 1 for Y1. Real value is 1 for Y1. Imaginary value is basically this circle which passes through like this, right? So that imaginary value, when you mark it, you will get it as 1 plus J 1.47. Now, that was one solution. So the length we can mark it as, let's say, D1. Now, instead of that, we can also have another solution as we discussed earlier. The load is from the load when you move along the VSWR circle, right? From the load point, when you're moving along the VSWR circle, again, you move further down, we'll reach another point Y2, which is located at, so from connect center Y2 and extend outwards, so that is located at 0.324 lambda, right? So from the load, which is located at 0.066, if you move a distance all the way up till this point, right, which is having a reference point, which is having 0.324. So what you are just, am I audible? Right. Okay. So sorry, there was some issue with the network. Anyway, I'll share the screen again. Right. So as discussed earlier, so load is located at this location and Y1 is at this reference location and Y2 is at 0.324. The load is from center, connect the load, extend outwards and mark it as 0.066. Similarly, Y1 is located at from center, mark Y1, connect Y1 and extend outwards. In the outermost circle, we'll be able to mark a value of 0.176. So from load, if we move along the transmission line for a distance which is 0.176 minus 0.066, because starting values YN and final values Y1, right? We are reaching a point where the admittance is y1. So the distance between these 2 points will give you the length from the load location where we would find an admittance value as 1 plus 1.47j, right? 1 plus 1.47j is the admittance at y1. So real circle is 1 and imaginary circle we had seen earlier. Right? It goes somewhere over here, and we'll mark the imaginary value as 1.47. Now, for y2, right? y2 is located at 0.324, which also which also is common for both 1 plus j circle and VSWR circle. So from the load YL location, if you move along all the way till the y2 point, right? When you are moving along, so from 0.066 lambda reference location as YL, right? YL is located over here. When you move along a distance all the way up till so YL is located at 0.066 lambda. When you move along the transmission line to a location of 0.324 lambda, we would get an impedance value admittance value corresponding to 1 minus j 1.47. Right? Yin will be reading or y2 will be reading a value like this. Right? Now in both the cases, real part is 1. We are trying to find the imaginary aspect, imaginary concept, basically the susceptance, right? Okay, so the length that you need to move from the load for the second solution is 0.324 minus 0.066 lambda, right? Then, yeah, I have given it over here. For the second, it was 0.324 minus 0.66 lambda, which is 0.258 lambda. And in the previous case, from y1 to reach y2, we are moving a distance that is 0.16 lambda final value minus the load location, which is 0.06 lambda. We are getting a distance of 0.11 lambda. Right. So now at y1 we have admittance as 1 plus j 1.47, and at y2 we have 1 minus j 1.47. Right. So in the problem, we need to match it or tune it using short circuit stub. Right. So the stub needs to be having a short circuit that we are going to connect in parallel at y1 location and y2 location. So first we'll take the solution 1, right? So y1 is located at a distance of 0.11 lambda from the load, right? So d equals 0.11 lambda. The admittance value at y1 is 1 plus j 1.47. Now we have an imaginary component over here which needs to be cancelled out with minus j 1.47. So this needs to be added using a parallel stub, which is having short circuit as termination. Right? The termination is short circuit. From short circuit, we need to move to a point where our stub's admittance will be equal to minus j 1.47, the one with which we are going to cancel out the reactive part of y1. Right? So for cancelling out, we are actually having this stub getting attached in parallel. So starting point is short circuit and ending point is minus j 1.47. So minus j 1.47 is nothing but 0 in real and minus j 1.47 in imaginary component, right? So 0 is basically this circle, right? Outermost circle. So in the horizontal axis, if you see, the real values are just given over here. So 0 is basically this outermost circle, right? So 0 minus j 1.47 will come somewhere over here between 1.4 and 1.5, right? So at this place, we will be getting minus j 1.47 point. So connect this. This will be the stub's impedance, right? Now stub's in a final position will be over here corresponding to the stub that we are going to connect at y1. So connect the center point, this stub location and stub impedance, stub admittance, and extend it outwards. This will give us a reference value corresponding to the Y stub. Now, what is the starting point of the stub? Short circuit, right? We are using a short circuit stub. So in short circuit, impedance in short circuit is 0. Admittance in short circuit is infinite. So all the values, earlier I told you that all the values in the Smith chart right now correspond to admittances. Hence, the rightmost point that we have is the short circuit, which has the admittance value y equals infinity. So this is going to be the starting point, right? The rightmost point in the Smith chart is going to be the starting point. Now, if you see in the outermost circle, you'll be reading a value of 0.25 in the rightmost point. So starting from 0.25, we need to move along a distance all the way up till where we have an admittance of 0 minus 1.47. So in this way, we are moving from the short circuit of the transmission line, right, of the stub. From short circuit, we are moving to a point where stub admittance is minus 1.47. So again, with respect to the values, we'll see in this slide. Yeah. From short circuit point, which is at 0.25, we are moving to a location where the admittance value is minus j 1.47. So minus j 1.47 is located at 0.346 lambda, right? So this point is located at around 0.346 lambda. When you extend it outwards, connect this center and this point, extend it outwards. So where it passes through, so that is going to be 0.346 lambda. Now that is the final point. Starting point is the short circuit point, which is the rightmost point of the Smith chart, right? So connect the center and rightmost point, enter, just expand it. So 0.25 is the starting point. So from starting point as 0.25 for the short circuit, we are going to a point where admittance value is 0.346. So 0.346 minus 0.25 lambda will give us a length of the stub as 0.094 lambda. So the length of the stub, this is how we are calculating as the stub length, which needs to be connected at Y1. Right? At Y1, we had the admittance value as 1 plus J 1.47. Hence, to cancel out this admittance of plus J 1.47, we are moving up to a point from a short circuit to reach a value of minus J 1.47. Now, again, just to clarify, we are using short circuit because in the problem it has been given. So if it was from open circuit, then you need to find out the open circuit point in the Smith chart, right? So what is open circuit point? Impedance will be infinity, admittance will be 0. Since all the values are in admittance in the Smith chart, you need to locate a point where admittance is 0. So that I left up to you. Now, the solution we had found out was at Y1, what is the stub that you need to find? Now, what about Y2? So we have another solution. For Y2, the admittance value is 1 minus J 1.47. Right? We need to cancel out this minus J 1.47. For that, we need to have a plus J 1.47 as the stub, right? A stub admittance. So the susceptance of the stub should be plus J 1.47. Again, we need to start from short circuit point. The short circuit point remains the same where y equals infinity. So connect the center and the rightmost point, extend it outwards. The starting point is 0.25 lambda. Now from here, we need to move all the way along to reach a point where admittance is plus J 1.47. What is plus J 1.47? It's nothing but 0 plus J 1.47. So 0 resistance, the normalized resistance is nothing but this circle, but I'm just marking it over here, right? Because along the horizontal axis, 0, 0.1, 0.2, like this, all the values are listed, right? So 0 is the outermost circle along the Smith chart. So at this 0 resistance, part and the zero conductance part, and susceptance as 1.47, it actually passes through over here. At this point, J1.47 is over here. So connect the center and connect this J1.47, extend it outwards. So that will give you the final location, right, where it should, final location of this stub, where we will find J1.47 as the plus J1.47 as the admittance for a short circuit stub. So we are going to start from the short circuit point, and we are going all the way along the outer circle, right? So up till J1.47. So we are covering half circle, like a semicircle, when we come to the leftmost extreme. When you are starting from the rightmost point and when we are reaching the leftmost point, right? We are covering half circle. Again, in previous videos also I have told, when you are covering half circle distance, we are moving a distance of 0.25 lambda, right? And then from here, additional length of whatever is given in the top scale is basically moved, right? We are moving a distance as available in the top scale. So the net distance that we have moved is 0.25 lambda plus 0.154 lambda from short circuit point to reach a final point. So from the short circuit, we need to move along the transmission line for a distance of 0.394 lambda. Right? For half circle, it is 0.25 lambda from rightmost point to leftmost point. Then when you move further from here till J1.47 plus J1.47, we are moving a distance of 0.154 that can be seen from here in the outermost circle, right? So in total, we are moving a distance of 0.394 from the short circuit to find a stub impedance which is equal, stub admittance which is equal to plus J1.47. So when we attach this stub in parallel, right, plus J1.47 stub is available from the short circuit at a distance of 0.394 lambda. So this one, when we attach to Y2 point has 1 minus J1.47 as admittance. Now we are attaching this parallel stub, which is having an admittance of plus J1.47. So in total, the total admittance seen over here will become 1 plus 0J, which is equal to 1, which is equal to the characteristic admittance of the line, meaning we will have matched condition, right? So there are two solutions again. So first, this is the load. So to the load at a distance of 0.11 lambda, we are having Y1 point, and from the load in second solution at a distance of 0.258 lambda, we are having Y2. For Y1, the admittance was 1 minus J1 1 plus J1.47. So what we did, we selected a stub length in such a way that from short circuit, we are having, right, from short circuit, we are having a stub admittance which is equal to minus J1.47. So this, we connected it over here to cancel out this admittance at Y1, right? So we had from the short circuit at a distance of 0.094 length, we are finding an admittance value of the stub as minus J1.47, which has been connected to cancel out the admittance, the reactive part of the admittance as, the susceptance part of the admittance, which is, so plus J1.47 of Y1 is cancelled by minus J1.47 of the stub in the first solution. In the second solution, Y2 point was 1 minus J1.47. To cancel out this minus J1.47, from short circuit, we are having a stub admittance corresponding to plus J1.47, which we just now cancelled. So this length is 0.394 lambda. right, which is given out here as the solution number 2. Right? So this is how we determine the length of the stubs correspondingly, and the frequency dependence again. So load impedance is 60 minus J80 and matched condition at 2 gigahertz operational frequency. Right, so frequency is 2 gigahertz. The reactance is, so for the load in the problem, the reactance part is minus J180. So J80. So J80 is nothing but J times XC, right? With the minus sign. That's why we are writing it as XC. So XC is because due to a capacitance, and if we calculate, we substitute the frequency in XC. So XC is 1 by 2 pi FC. So XC we substitute over here, frequency we substitute over here, we'll be able to get the capacitance value as 0.999 picofarad, almost 1 picofarad, right? So 0.995 picofarad. So this is in series with the resistor. Now, as a frequency response, when we see how this would create an input impedance at different frequencies, right? So previously at 1 plus 1 minus J 1.47 and 1 plus J 1.47 at Y1. This was at 2 gigahertz. At different frequencies, Yin would change. Right? It would not be exactly 1 also. The real part will be offset. Now, because of that, impedance mismatch will be there, and that would be observed in the reflection coefficient that has been plotted. Right? Reflection coefficient as a function of frequency for this existing length, fixed length that we have corresponding to 2 gigahertz, right? So the reflection coefficient will have different values for both the solutions. Right? Solution 1 has a much wider bandwidth when compared to solution 2 because in some cases we'll limit the reflection coefficient, operational reflection coefficient to 0.2. So let's say, meaning the solution 1, more range of frequencies we can operate in permissible with a permissible reflection coefficient. Whereas solution 2, very less frequencies are permitted within this magnitude gamma is 0.2, right? Which is smaller than 0.2. Now, that's basically the inference from this plot. Now, in case if you are interested about the mathematical aspect of how we can determine the length, so that is given out here. So that one, I'll leave it up to you for you to go through that, right? So you can just take a screenshot or pause it and probably derive it. So I'm not going to explain it right now. So you can just take it up for your exercise if you need, okay? So again, go through other videos given the description. One is for series stub and another one is for the Smith chart. And again, follow this channel for other simulations using Ansys or CST. Again, I'll be putting up multiple videos in the future. Yeah, thank you and all the best.